Okay, hi everyone. Welcome to the last Quantum Club of the semester. So tonight, the Quantum Club given by Thew about quantum internet. And as usually, we have a warm-up talk, and tonight it's given by Elisa, which is also a member of the committee of the Quantum Club. So thank you both, and enjoy.
Okay, yeah, welcome everybody. So I'm going to talk, give you a bit about an introduction about entanglement and quantum repeaters, if you're not familiar with that. First, I thought I would give you a brief introduction to a bit of history. Now, what I hope all of you, at least most of you know, is that we had something called the Industrial Revolution. Basically, this was the time when we had the invention of the steam engine and mass production, so very influential period for productivity. But it didn't stop there. We had something called the technological revolution, which is also often considered the second industrial revolution, where then we had things like electricity coming in. So we had machines which also automated the production process and the mass production. So yeah, this was also definitely very relevant to today's world. Then followed what is also often considered the third industrial revolution, which is the digital revolution. This is something which I'm sure you're all familiar with. I mean, this is then when information started to play a role, and we got things like the computer, which I guess almost all of you have a smartphone in their pocket right now. So we can see how that is very relevant. And somewhere between this technological revolution and this digital revolution, at the beginning of the 20th century, is where quantum came in. So, especially in industry, a lot of people like to talk about the quantum revolution. So what happened was the development of quantum mechanics, this is like by people like Einstein, Schrödinger, Max Planck, etc. And this definitely also played a role for the digital revolution. If you think about stuff like lasers and transistors, which are definitely also related to quantum mechanics, which would then definitely play a role for the digital revolution. And now something is happening, which is in the industry is often called the second quantum revolution. And so you might wonder what's the difference between the first and the second quantum revolution. Well, it's quite simple. The first quantum revolution, things like lasers, we're still talking about many, many photons. So while we're using quantum mechanics to explain what's going on, and it was used for the development, we're actually not using all of the properties that quantum mechanics has to offer. And so this is then something which comes in at the second quantum revolution, which is basically where we're at the moment. So for those of you who may not be that familiar with it, what are some of the properties? Well, the change between classical and quantum is that in classical we talk about bits. I mean, in computers we have bits, we have zeros and one, which is basically most of the time just either something turned on or something turned off. And now in the quantum regime, we start talking about qubits, which can also be 0 and 1, but which has the great advantage that it can also be basically everything in between. Like any linear combination between 0 and 1 is a valid quantum state, as long as it fulfills this condition, which is basically just, if we measure in the basis of 0 and 1, we either get 0 or 1 with a certain probability, which is proportional to those coefficients that we choose. And so everybody that paid attention in statistics knows that this probability should definitely not be greater than 1, and if it's less than 1, there's also generally a problem. So let's keep this at 1. And so this state is what we call a superposition. This is pretty general. I mean, we can, for alpha and beta, we have quite a lot of freedom of how we can choose those. So this is what we have for one photon. And so if we now move to example the description of two photons, we might have two very general states, right? Two superpositions. This is basically the most general state we can write in this basis for a single photon. So the intuition might be, let's just combine them, just make a product, just put them back to back, description independently. But as it turns out, this is not the most general state that we can do. Because as it turns out, there are states like those states down here, called Bell states, and those is what we call entangled states. And if you haven't done that already in quantum mechanics or any other class, I would highly encourage you to try to express this as a product state. It's fun, but you will fail. So yeah, this cannot be written as this. And so this tells us something about how those photons are correlated in a way, and in a way that is not possible with the classical state. And so those Bell states play a really fundamental role in quantum information in a lot of applications. And we will shortly see why. But before that, I would like to bring up a very current topic. So Christmas is coming up, so we might have a situation like this. We might have Santa Claus, and we might have like a Christmas tree or kids or whoever wants to get the present. And now everybody who has sent a sufficient amount of packages via post knows that they don't always arrive. Now whether that's the Grinch or just some coincidence, now that's up to you to decide, but let's assume for now it's the Grinch. And so if we send this via post in a very classical way, well, occasionally something might get lost or intercepted. So can we find a solution to that? Now the bad news ahead of time, classically no, I can't solve those problems for you. But everybody that has watched Star Trek a sufficient amount of times might remember things like teleportation. So it would be pretty cool if we could just do something like taking the present from Santa Claus and just teleporting it underneath the Christmas tree. Would also solve the whole chimney problem. Just like this. And so this is what we want to do. And the neat thing is that this is kind of possible in quantum mechanics. So instead of a present, because it's a bit large for quantum mechanics, we're going to talk about a state. So once again, we're taking the most general state possible, and we're going to take one of those entangled states that I spoke about earlier, the phi plus Bell state in this case. And so for now, they are completely uncorrelated. I mean, they're just part of the system that we're going to describe, where we want to send something from A to B, with which are entangled, which share an entangled state. And so the general state can indeed, in this case, be written as this product state. Which then looks something like this. And now we can do some playing around with it and basically rearrange this in a bit. And what we can see is that we can actually rewrite this in a way that we get the Bell states not as an entangled state between A and B, but as the state that we want to share and the part of the entangled state that A has. So there's all those Bell states. And B then also has some state, which in this case it's quite obvious this is exactly the state that we want to send. In those cases it's quite similar, but it turns out we have to perform some transformation on this, and everybody that's familiar with the Pauli matrices might realize that this is exactly the transformation that we need. So either sigma z or sigma x or a combination of both. And so now if we perform something called a Bell state measurement on A side, on the state that we want to send, and the entangled state that we share with B, we can basically get out which state is on A side. So which of those Bell states do we have? And from this, we then automatically know which state B has. So the problem is, B doesn't know that. So we're still going to need a classical channel for that. And this is where basically our speed limit comes in, because general relativity still holds. And so what we can do is, by using this classical channel, we just have to send 2 bits, because we have 4 possibilities, to tell B which transformation it has to perform to recover the state that we wanted to send initially. And by looking at the definition of teleportation, this is more or less exactly what is teleportation. I mean, we instantaneously travel the state between 2 locations without ever having sent a photon with the state between A and B. So what can we use that for? So this is a scenario which we also more or less use every single day. So if you think about the internet, we send light through optical fiber to transmit information. But a problem that we have is that optical fiber has loss. And so what we use in classical physics is something called a repeater, where we basically amplify the signal again so that the losses kind of get compensated for. Now, sadly, even though quantum mechanics offers us some nice things like superpositions and entanglement, there's also some downsides. For example, the no-cloning theorem, which means that we can't just take the photon that we want to send and clone it and multiply it. So that doesn't work. So what do we do instead? We basically do what we just described with the quantum teleportation. But instead, we do something called entanglement swapping. We basically have here in the middle, this is basically our repeater, and we share an entangled state between A and the repeater and B and the repeater. And now by performing a Bell state measurement in the middle, we basically swap the entanglement between A and B. Now, the math is basically the same thing as in the case for quantum teleportation. So if you're ever bored, feel free to try it. And so then, instead of having a scenario like this at the moment, if we know the result of the Bell state measurement in the repeater, we basically share an entangled state between A and B, just with a step in the middle. And so if we do this in an application, this is basically the same as a quantum as a repeater, so a quantum repeater. And if we do this many, many times, well, then you can cover quite a lot of distances with shorter segments, like in the case of the classical repeater. And so if we could do this in real life, Christmas would be saved. Thank you for your attention. Questions?
I think
okay.
Then start again. No, it really is a pleasure, and I just want to thank the Quantum Club. You've been doing amazing stuff, and it's really cool to see everyone making this effort and getting interested in quantum. Actually, just the quantum revolution, the second quantum revolution. We were just talking before coming here about my previous life, and the people that invented, well, I think can take credit for that, Gerard Milburn and Jonathan Dowling. And Gerard used to be my master's supervisor. That's my touch to fame. Okay, this I think is the most pretentious title I've ever used. And I did hesitate a long time about using this for at least one big reason, and that's because building the quantum internet one photon at a time. I don't like using the term quantum internet, but you will see and hear this talked about all the time. So I thought I'll use it. I have your attention, and that's why it's called the quantum internet. But what I like to think about is what it really means, and what it means is what we've been doing for the last 20 or 30 years in quantum communication. So the quantum internet, the way I see it, is really just dealing with developing applications and uses that exploit quantum correlations or entanglement. And you see, it's not nearly as exciting as the quantum internet already. But your quantum internet works. I'm going to sort of put it in the context of quantum networks because that's where I feel comfortable talking about. So what are quantum networks? And what can we do with them, I suppose, is a good question. So these are some of the things that we're looking at here in Geneva and in general in the community of people working in quantum communications. And it really does bridge your sort of fundamental to applied physics, research, development. It really takes everything from going from industrial things like standards for quantum technologies, to security proofs, both in the lab and in real-world scenarios, what we call end-to-end security. It deals with a lot of technologies, photon detectors, quantum sources, and then there are all sorts of applications going across different network architectures. air-based things. People are putting communication systems in aeroplanes, in balloons, satellites, which are somewhere here, yes. And increasingly more complex networks, multipartite networks, with the goal of sort of some ideal quantum communication network across the globe. And that will probably involve quantum repeaters, which we just heard about, satellites, and that's a little bit the vision of what we're trying to do. On technologies, I've got dimension memories, but I'll come back to that. What's cool about this is I used to present this for like a general motivation slide for quantum communication. Actually, we're working on just about all of those here in Geneva. Maybe the cloud-based quantum computing, not so much, but there's a group of people in the building across the road really sort of pushing all of these different applications and technologies. So we just heard about quantum repeaters. So, I mean, we do a lot of applied QKD and things, and more applied things, but I want to focus today on entanglement, because if we're going towards quantum repeaters and really sort of global networks and sort of distributing quantum resources such as entanglement and correlations, we generally need to think about entanglement at some point. And so this is a sort of bit of an exploded view of what Elisa was showing us before about these entanglement links. So in each of these links, we have our sources, we have maybe some quantum memories. And indeed, Mikhail Celius is doing some amazing work over there with that. And if you're looking for speakers, he's a good speaker and he's really one of the world leaders in this field. What we call quantum frequency conversions, because maybe the wavelengths of different things in the system are different, so we want to try and make them indistinguishable. We have to worry about distance, and then we have to worry about synchronization and stabilization. So we spend a lot of time working on the technologies to put into these networks, but all the time what we're thinking about is how do we build a system that's going to really operate all together in a distributed scenario, in real-world environments and stuff like that, even if it's today only more basic research than applied. So what I'm going to try and do, the other bit of the introductory title was building the quantum internet one photon at a time. So one photon at a time. I'm going to sort of give you a very hand-wavy introduction to how photons are made. Then I'll talk a little bit about how to make good photons, what that even means. And then we'll start to get a bit interesting. We'll sort of use that to show a simple entanglement, and then we'll get more and more complex, and we can see where that gets us. And if I'm getting too fast, too detailed, or not detailed enough, please stop, ask questions, or pull me up and ask me to explain what I mean. So, photons. We all know this is what a photon looks like. How do we make that? Well, we use sort of technologies, systems, and they're various, and depending on what sort of photon we want, we might choose different materials and different systems. But in the end, what we really want is something that spits out one photon at a time. I do anyway. And there are multiple ways of doing this. From atomic systems, which has historically been a great source for that, but more recently sort of artificial devices where you have defect centers in solid state materials like NV centers, if you've heard of that. Quantum dots are sort of artificial atoms that are made out of sort of materials like indium arsenide. We're sort of still using, to a large extent, what we call sort of probabilistic sources, which I'll explain in a moment. So the main one really is you're using nonlinear optical material. We send in a pump photon, or we send in a lot of pump photons, a huge laser, sometimes not so huge. And that breaks into a pair of sometimes called daughter photons. Two photons that are correlated in energy. So the pump has a certain energy, and it breaks down into these two signal and idler photons, and they have to conserve that energy. We're not putting any energy in or taking any energy out. The other variation on this sort of process is what we call spontaneous 4-wave mixing. And like here we had 3 waves. Unsurprisingly, we have 4 here. So that's about as far as we go with this. We can go further, but so signal and idler, again, energy correlated, and also correlated in time, which is one of the few entanglement degrees of freedom that we can actually get sort of almost naturally. So they could energy conserved correlations of the signal and idler, and because they're created at the same time, we have very good timing information between the 2 photons. Delta T is approximately 0 for argument's sake here. Okay, so as I was saying, we get this energy time entanglement for free. But there are lots of other degrees of freedom we can use that can be entangled. But the trick is people always talk, I have something that's entangled. It's like, always need to ask what's entangled. So here it's energy time. We'll come back to other things in a minute. It'll be polarization or the classic one. But what I want to focus on here is coming back to the single photon thing. How do we get 1 photon? Well, I just told you that these photons are correlated in their creation time. So if I detect this signal photon, I know that there's a photon in the other mode, the other arm. So I can herald the arrival of this idler photon. So the system is probabilistic in the beginning, but once we get a heralded single, we know with some probability that it's there in the output arm. But now we want to think about how good is this photon? And so there we need to start thinking about controlling the different degrees of freedom. Is the polarization well defined? Your other wavelengths well defined? Where are the photons in time? At the moment I've only got 1 photon, but when we start to have 2 or 3 or 4, this timing will become important. And there's also some really cool games you can play with the spatial modes of light, but we don't play with them. I'm not going to talk about them, but it's just such a cool picture. So these are the things we really sort of need to think about, sort of engineering, managing, and the more we can do at the source, the better, but in the real world, we have to sort of make sure we keep track of what's going on in all these degrees. So I'm really grateful for Elisa describing teleportation, because she had all these equations and I really tried to not have any equations, but I have some. But nothing like her slide, which is useful and informative, and it was a great intro. So I'm really grateful you did that and I didn't have to. So before I had this, a dagger acting on the vacuum, sort of my 1 photon state. Well, what does that 1 photon look like? And you can sort of describe that, let's say, in terms of this spectral function here, which again, big equation, looks messy. We'll come back to that. But the way we look at a photon, it's say in terms of its spectrum for the moment, that's just that degree of freedom. So we can look at this pair of photons, this signal and idler, and look at the frequency components of all of these things. And what that maps out is this sort of, what we call a spectral, joint spectral amplitude. And what's going on here is, depending on your pump bandwidth, bandwidth of your laser that you might be driving the system with, and the phase matching condition of this nonlinear crystal, this is what we can really engineer to sort of control the shape of the photons coming out. You get this distribution of photons. And it's not obvious, but that's not very good for what I want to do. So now how can we control that? Well, this ugly equation down here, well, we can really break that down into some part that's really just describing the laser. Another part that's really describing the phase matching of the system. And another part which we can sort of add on top of that if we want to do some spectral filtering to sort of take a brute force approach to changing this joint spectral amplitude. And what a filter is really doing, if I put 1 arm, I get a cut out of this graph like this. But what we want to do really is sort of engineer or filter, if we have to, something that comes down to sort of a simple circle in this space. And what that does, it means that there's no correlations in frequency. Elisa had another lovely equation where she challenged you to sort of write an entangled state as a separable state. So the thing here is, in this huge, long, elongated ellipse, there's lots of entanglement, but in frequency or in wavelength. But now, in this space, we're actually separable. These frequency components are separable. We have no entanglement there. And that's really interesting, because if we want to entangle with other things, we need to have this separable state, because we don't want it entangled with anything else, because there's something called the monogamy of entanglement. And if you're entangled with one thing, then you can't be really well entangled with another. So we want to disentangle ourselves from everything we can. So that's how we can do it. And really, we really want to concentrate on these two, because this works, but typically filters introduce loss. So we don't like loss. We have enough of that. So how do we test this? So this is a sort of typical sort of setup we use. We have our nonlinear crystal, we have a pump, generates a signal and an either over here. And because I eventually want lots of photons, I can turn that pump around and send it back the other way and create more photons. These photons and these photons aren't entangled, but these photons are entangled and these photons are entangled. But as I said before, what we want is this joint spectral amplitude or joint spectral intensity to be sort of a circular shape in this space. And here it's pretty circular. So it means we're in this sort of regime that we want to be in. And what that means is we can start to interfere these photons, or even this photon with this photon, or this photon with this photon. And actually that's what we see here, is the interference between two photons. And the more indistinguishable they are, and the rounder this is to a certain extent, the deeper this dip is here. So this is what we call a Homu-Mandel interference curve. And ideally we want this down to 0, which means we have a visibility of 1, and we can say this is a perfect single photon source, and so is the one next to it. So this is a bit of a workhorse for us. This is a sort of core element to a lot of experiments, some of the experiments that I'll talk about here. But this is probably something you may not have ever seen. So here, what's going on? I said Homu-Mandel interference. What does that mean? Well, we talked about indistinguishability. So if I've got one photon here and one photon here, what happens? We can go sort of straight through. So we get a 1-1 term, or both could be reflected. We get a 1-1 term. Or what happens here? They cancel because of the phase there. So the other option being that this one's transmitted and this one's reflected, or this one's transmitted and this one's reflected. And if they're really indistinguishable due to the quantum interference taking place here, we can really remove these two terms and get that. And what does that mean compared to this? So here before, remember we were looking at coincidence measurements. We wanted to detect two photons. Should go back. So we want to take two of these photons, either this one or this one, and put them on a beam splitter. Like this. So these two photons are coming from either one of the sources I just had, totally independent. And we look at the coincidences here. And as I said before, okay, we got this. I'm never going to see these 1-1 terms because the interference rules them out. So I'm out here, my timing is off. So they're distinguishable in time. I can tell which one goes which. There'll never be any interference here. So I get some coincidence rate. But as I remove this time difference, so before we worried about spectrum, now we're worried about time. I remove this time difference, and as they become indistinguishable in time, these 1-1 terms disappear until eventually I just have these states, And if I've got 2 photons here and 0 here, I'm never going to get a coincidence. So this is a fairly straightforward way of characterizing the quality of our photons, but it was actually introduced a very long time ago, depending how old you are, to measure your in time intervals at a very precise level. But it is one of the most important fundamental tools in our toolbox for quantum information and quantum optics. And it's critical for the Bell state measurement we heard about just before. So, now we've seen photons, we've seen beam splitters, and really in terms of optics, that's simple as it gets. And so we know what happens, we get a reflection or we get a transmission. And that's just due to the beam splitter operation. So we're used to that. It's simple. We can look at that a little bit differently. So there's one photon went one way and the possibility that one went the other way. So now we have a situation where if we think about this a little bit differently, we've got a photon here, which means the vacuum, which is still coherent with it at this moment, is over here. And we also have the possibility that when the photon went here, the vacuum is over here. So we can write this state a little bit differently and it starts to look like an entangled state. And if you don't believe that, that's why it comes under many names, but the last one here is was a point of great contention, and there's still people wandering around asking this question. But it is entanglement, and it's very simple to see because if you put an atomic system at the end here, you can have a ground and excited state. If the photon hits it, it's going to go to an excited state or not. And everyone believes that 2 atoms can be entangled. Maybe you don't, but you should. So here, I'm pretty happy that this is an entangled state and very easy to generate. But now we come back to the single photons again. So this was one of our heralded single photon sources. And we've just created entanglement with it. So not only do we have heralded single photons, now we have heralded entanglement. And this is really cool because most entanglement is probabilistic. So now we've got heralded entanglement. Is that useful? Oh, actually, one thing about this entanglement, because there's only one photon and we're playing with the spatial modes, we can really just introduce more and more spatial modes. And then all of a sudden, instead of having an entangled qubits, we've got instead of Alice and Bob, we've got Alice, Bob, Charlie, and however many parties you want. So this is multipartite entanglement, and this is something that's very cool for networks and things like that. And if we're playing with fiber, this is almost trivial because Telecom invented these great things called multi-port couplers. So you come in with one mode and you get out however many fibers are there, and you've got free multipartite entanglement from one photon. It's more complicated to measure, but that's another talk in itself. Okay, so now we've got entanglement, we've got heralded entanglement, that's cool. We heard about teleportation, also very cool. And we can do the same thing here. We start with our single photon here, we encode our qubit like we heard before. We already know we have entanglement here. Okay, we've gone from heralded single photon entanglement to teleportation. And as Elisa pointed out, if this is not just a qubit but an entangled state, we can go to entanglement swapping, or teleporting entanglement, teleportation, as you like. So already we've just made a huge step. We've gone from just one photon to a heralded entanglement to teleportation to entanglement swapping. You see, you have a lot of the key ingredients for attacking this problem of quantum repeaters, which again, Elisa gave a wonderful introduction to. One thing she didn't mention was, well, she did a little bit, was we need this because we don't have quantum amplifiers. But why we need it is because even fibers which are relatively low loss have loss. And if you go over 1,000 kilometers, that loss is really quite a lot. So if you've got like a 10 gigahertz laser, you're sending a photon, you're at gigahertz rates over 1,000 kilometers, you're going to have to wait 300 years for a photon. That's not really high bit rate if you want to do sort of some video encryption or anything like that. So that's sort of underlying motivation. And the ideas for that came up again, sort of 98 and 2001. A couple of very similar ideas. And, as was heard before, break this down into multiple links, make these Bell state measurements, join them together, and progressively we can sort of spread out over longer and longer distances. One thing that I'm not doing in my group that's essential for this is quantum memories. But as I mentioned before, Miguel is doing that side of the puzzle for us. So, how do we do this? And what are the challenges? Because it's easy to draw stick figures and balls on the screen. There's still stick figures, but we'll get there. So we have our couple of sources as before. We have our sort of beam splitter, Bell state measurement, whatever you want to call it. But we want to do it in the real world, so we've got to worry about this timing question. So fibers actually don't stay the same length. They heat up, they cool down, they vibrate. So this is a problem for having this interference at this beam splitter that we want to have. So we've got to work out some way of maintaining that. Also, the fibers, going all over the place. They could be actually hanging in the air and swaying through in time. So we need to have some way of controlling that. We need clocks everywhere we have some system because we want to synchronize these things. We want to know when someone generated a state and when we detected a state. But if we sort of take, for example, the case we were talking about before, we have maybe some probability of generating a pair here and a pair here. When we get our entangled state over here, based on one heralding detection in the middle, we've got a way of building that first elementary link of a quantum repeater. But one of the big challenges in doing this, with this sort of entanglement, is here. I haven't got the phase written in here, but this is phase dependent. So I need to make sure that this, what is basically a large interferometer, possibly spanning tens of kilometers, is phase stable. And you might think I'm crazy if you wanted to do that, and I am. But it has other advantages, so nothing, you never get anything for free. So this was our toy setup for doing this. We have our two sources, we have a pump. As I said, you're pumping both. We actually, we have Alice and Bob, we have our detection. We talked about the phase stabilization. I'll talk a little bit about here. We actually do quite a few things here. DFG stands for difference frequency generation. But basically all we need to worry about today is that we're sending in another laser here that we will use to lock this interferometer. We also use it for the measurements, but that's again another talk. In practice, this is a simplified version. And you don't want to see the table that it's sitting on. Well, maybe you do, and you're welcome to come and look. It's not exactly that experiment anymore, but it's the way it is. So here's our pump laser, here's our two crystals, our two nonlinear crystals generating our pairs of entanglement here and here. And this is our giant interferometer. In this case, it's just a couple of kilometers in the lab. We're not in the real world with this experiment at the moment. But you see some feedback loops here for the phase correction. We can tune the phase in this system and control this really quite well. And to give you an idea of how quickly things sort of can move, okay, this is just some calibration steps to look at the loss in each of the paths, path 1, path 2. If we do no phase locking, this is what we're detecting. We can see that if we have this 0, 1 plus 1, 0 state and the phase is fluctuating this fast, it's basically just a mixed state, and we're not going to be able to do anything related to entanglement. But once we do lock the system, this is where we get to, and this is really sort of stable. So I said this is only a couple of kilometers, and that was limited more by, we could certainly do 20 kilometers and probably even in the field now, but it was practical problems. So that works really well, certainly well enough to get going. And as I said, we can tune this phase. We have what we call an entanglement witness, as some way of sort of determining whether the state you've distributed is entangled, just based on some correlation measurements. And we can see if we vary this phase, not let it fluctuate, but just tune the phase so we're really at this state that we want. We're able to violate this, this entanglement witness and claim that the system is not only stable, but actually still entangled. But yeah, what I didn't mention, and people mostly never mention in this quantum repeater chain thing, is that's just one link. It's one photon entanglement over this long link. Typically what was done in the original paper, and everyone's forgotten, is there's a second link. Because the idea was that you call this top link horizontal, and you label this bottom link vertical. And then you could do another Bell state measurement between your H and V photons, and you suddenly have a polarization entangled state that you can measure with good fidelity. And so why is that interesting here? Well, I mean, that's sort of your more complicated building block for a quantum repeater. And that's what we sort of wanted to see if we could build out of single photons. So we have our single photon V entanglement here and here, a single photon H entanglement here and here. But we still have this huge phase that we've got, a huge interferometer, we've got to lock the phase. But now we're thinking about polarization, we can actually multiplex them in the same fiber. They won't sort of see one another in a sense. They're orthogonal states, they won't bother one another too much. So now I don't have this huge interferometer. I've got both photons traveling the same path, so they're going to pick up the same phase fluctuations and whatever. I'm cheating a little bit because in practice what I want to be able to do is herald the horizontal and the vertical modes at different times, because I'll distribute into my quantum memories the entanglement. I'll wait for my horizontal to be ready, and then I'll wait for my vertical to be ready. And then when they're both ready, I have this entanglement. And so I need to stabilize the phase during that time. But here, proof of principle, no memories. Again, it looks a little bit scary, but not too much. We have our source here generating our photons again. We use all 4 photons actually here, but we don't do the heralding until we get to our central station. I'm not going to explain how this works because that's probably 15 minutes. But what we see is it distributes good entanglement. I talked about heralded entanglement before. That was just local. Now, because I'm doing this swapping, and I've got all this beam splitting and stuff over here, and the detection for Bob, all local, let's say, all on the same table, I can keep the losses really low. So when I get a click here, I have very little loss here. And actually, I can tune how much loss I have by making this highly imbalanced. So if I force all of the photons to go here, maybe 99% of the time, I don't get very many heralds, 1% times 1%. But when I do, there's almost no loss here. It's like 99% fidelity. So that's why we want to do it. So, does it work? We test to see whether we're indistinguishable. This is all of the different photons doing their homomantle interference again. We can do all sorts of measurements to reconstruct the density matrix of this entangled state, and here we find sort of 95% fidelity. So it works really nicely. In a post-selected way, I wanted heralded entanglement. That means if I get a click here, the state here is really entangled. But I have a probabilistic source, there's a lot of vacuum. So a lot of the time I get a click here and I've got nothing here, which is not what we want. So we did some simulations, tuning this beam splitting ratio to make the state higher fidelity. And if we have a perfect source, we can tune this and we can get up to really high fidelities, 80% fidelity, but then we get a drop off. It's quite interesting, but a technical point I don't think we need to go into here today. But even with a perfect source and sort of the losses we have in a current experiment, sort of a little bit more realistic, we're still only able to get to like 20% fidelity because of vacuum and things like this. And in practice, because we're using these probabilistic source, we've got a 2% fidelity, which is a long way from 100. So we've got some work to do, but the deterministic sources will improve significantly, and we can improve the local losses quite a bit still as well. So it's encouraging, but this is something we need to look at that's partially fundamental, partially technical. But we're limited by the multi-pair events. We're limited by how good the beam splitters are and the probabilistic sources. But I didn't go into this. We talked about QKD. You can use entanglement for QKD, quantum key distribution. And there's a scenario called device-independent QKD, is where really it's a black box. You don't need to know how it works. You just trust the input-output correlations, and it's good. But you've got to meet thresholds that are very high in terms of performance. And one of them is loss or efficiency. And most systems won't work because once you go into the fiber, you're already losing too many photons to violate the bounds for this. But with this architecture, it's potentially a candidate for doing that. So, what next? As I said and complained about endlessly probably, SPDC is a probabilistic process, probabilistic source. You need around 10 to the 9 pump photons to get a pair out. But the problem is it's not just a pair. We have multi-photon events, so sometimes they're getting 2 photons, 2 pairs. As I said, this is quite small, and we can't just keep increasing the pump power because if this goes up, this goes up. So we just get more multi-pairs and more errors. So it doesn't scale well. What we're really interested in is deterministic single photon sources. Something that really is like a gun that you just pull the trigger and it just keeps spitting out photons. Because there, the devices sort of have really some high probability of having 1 photon and maybe some small error of having a multi-photon event. And already they can be quite distinct, quite a big difference. People have already shown like gigahertz clock rates for these things, so they can go fast. We can generate a lot of quantum states with that. They're starting to get performance levels that show that this really can scale well. And when I say scale well, what am I thinking? This is very much a rough sort of model for comparing SPDC versus these deterministic dots. And so what's on the bottom here is the photon number, and this is the events, multi-photon events. So your 2 photon events, we get 2 photon coincidences, the order of tens of thousands. But by the time we're getting out to 4 photons, this is indicative. I'm not generating at any point 4.2 photons or whatever that is there. It's just a guide to the eye. But at 4 photons, you're down to a couple events per second. So it drops off really quite quickly. Whereas for deterministic sources, in the ideal case, you're sort of out here. But even if you have like something that generates only at 50% and you have detection at 50%, you're sort of following this line. And here, we go from a few events per second, up to megahertz, just for 4 photon events. And even for 10 photon events, we've got hundreds of events per second. So we go on and scale up these systems and get more and more photons involved, this is going to be necessary. And it is necessary for your going past what we're doing at the moment, because this is sort of a little bit what we talked about, these elementary links for quantum repeaters, but this is the first generation of repeaters, conceptually the first generation of ways you can generate and distribute entanglement over large distances. They're always going to be slow, probably slower than we want. But your theorists are theorists, and they can find new and interesting ways of making life complicated for experimentalists. And this is an idea called all-photonic quantum repeaters. In principle, it doesn't require quantum memories, but it does require a lot of photons. It's very resource intensive, but potentially has high rates. I wrote gigabit per second, that was probably optimistic, but at very high rates. And there you're again starting out with many photons, many entangled photons. They're called cluster states. These are more complex entangled states, and our favorite Bell state measurements. And conceptually it's similar. You just chain these together and you can extend over longer and longer distances. And one of the ways of building up these cluster states is a variation again on the Bell state measurement, that which fuses you have a multipartite system and another one fuses them together, which is more or less what a Bell state measurement does to your bipartite entanglement. And then doesn't work all the time. Sometimes it just spits out something that's not entangled, but occasionally with some probability you get this much larger, more complex state. And the key element to doing that is more photons. You have, instead of your standard Bell state measurement device where you have your photons coming in and you detect, now you start introducing more complex circuits and introducing more photons or entangled photons, and you can really increase the efficiency from the, well, actually that's something we didn't touch on. We won't touch on it. But your Bell state measures are typically limited to distinguishing only about 50% of the Bell states. So by adding more and more ancillas, we can increase that up even beyond 75% if we add continuous photons. So it's really sort of going to be an interesting area sort of to develop in the next few years. And so with that, I think I'm thereabouts on time. This is the team. This is only half the team because I've presented results there going back maybe 10 years or so, and this team has evolved somewhat in that time. A lot of help from funding, but collaborators as well. We have a close collaboration with ED Contique, the company here in Geneva, to the point where these people actually work for ED Contique. Actually, Giovanni was 50-50 for a while. Now he's 100%. But they're employed in ED Contique and they're doing their research and working with us in the lab, and they're very much part of the team. We've just had Boris Korj, new professor, start with us. Also someone very interesting to get to maybe talk at the Quantum Club about some of the single photon detection work, which I didn't talk about at all today. Even if it's got the best pictures and the coolest. Anyway, we also like to have fun, so it's not all serious. And with that, we'll finish. I tried to tell you a little bit about where photons come from, or how we get our photons. Convince you with some stick figure drawings that we do some experiments, even if I didn't show you the fancy pictures of single photon detectors, and how we get from just one photon to entanglement to distributed entanglement, and a little bit of a sort of perspective, insight into where we think we might be going. So, thank you.
Question.
I have a question.
Yeah.
So when you're speaking about how you generate photons, so you said that we know very precisely the energy of the signal at Hitler because of energy conservation. But do we have some loss in the nonlinear material? Is it very negligible? Or
Do we have what?
loss?
Yes. Some more than others. It's that's where the complexity comes in sort of engineering your source. You're even in a bulk material where you're just sending a laser through a bit of glass, which most normally materials just look like a bit of glass. You will have some loss. Some materials have more loss, higher index of refraction, more reflections. You can play with your anti-reflection coatings on the end faces. Sometimes we start using circuits in these, or waveguides in these devices. Then you've got to worry about mode matching, or laser or fiber in this mode. This is why it's most of our battle, or a lot of our battle is really sort of loss and coupling. We have one device and we want to marry it to another device. We need to get photons from here to there. Loss is important. So in the generation itself, this is critical because when we talk about this probability of errors, multi-photon events and things like this, if I lose these photons somewhere else in the system, that doesn't change anything. They always existed. They existed from the beginning of the process. So there's a chance that if I generated the pair and I generated a double pair, which photon actually got lost and which photon did I actually get, or which pair of photons did I actually get? So you really want this first pair and not anything from this multi-pair event. So yeah, that will count no matter what the loss is afterwards. So it's really in the source. So you want to create and extract your photons, especially entangled photons, with the maximum efficiency possible. And people do that with like over 90, even 95% efficiency.
Other questions? I have a quick question. You mentioned the length of the optical fiber varies.
Yeah.
Is that just due to temperature, or like what effects play a role?
Generally temperature. Yeah, actually I don't have a plot here, but I mean, depending on the length of the fiber, you can have a meter in length changed. And sort of you'll see this for buried cables under the ground. There's a sort of inertia. They don't sort of move so much, but you'll see daytime, nighttime, the length changing. And yeah, if you've got aerial, fibers, and you're doing something in polarization, you can really just see the polarization swinging in the breeze.
Okay.
I have a very naive question. How does one have to imagine these long fibers in the lab just on coils?
Yes. Yeah. No, we have huge bobbins of fiber. We have a long-standing collaboration with Corning, who make a lot of the fibers that exist on the planet. And we have several hundred kilometers of bobbins in the lab of varying lengths, sort of some 50, some 25, some 10, some 5, depending on how far we can push a particular experiment that we use.
And the length expansion of 1 meter, that's over which total length? Some hundred?
I'm trying to think the expansion, the expansion coefficient of fiber. Can't remember off the top of my head. I want to say 10 to the minus 6 per meter or something like this. 10 to the minus 6. Yeah, I mean, we talked about phase before. If I have like a meter of fiber on the table, if in one of these interferometers and I don't stabilize it, it will fluctuate like that a couple of kilometers. I mean, it's really, at the phase level, obviously, is different to your just pure length in terms of at the micrometer scale. But yeah, I mean, our long distance experiments, we're usually dealing with time windows of 100 picoseconds or something like this. 100 picoseconds. So we can deal with a little bit of loss in a direct communication scenario. And when we go to longer distances, what we can do is play with the length of the photon, the coherence time of the photon. So if we can make a coherence time that's a nanosecond long, I've got more chance of overlapping on that beam splitter if the fiber moves less than a nanosecond. And for the quantum memories, that's where they're really useful. pluses and minuses always, but they have something like 10 nanoseconds coherence time or more-ish. We want them to get them a little bit lower. But that means I can tolerate your 10 nanoseconds, a bit less than 10 nanoseconds worth of fluctuations before I have to panic.
Do you have any plans on trying to use different computers like quantum dots or something instead of the USDC?
I've had plans for about 10 years. I've just been waiting for the people that have been doing all the work on quantum dots to get them to a performance level where I don't have to do as much. As I said before, one of the key things for me was sort of maybe recently a few different systems have hit coupling interfiber of 50%. It's great having deterministic photons, but if you lose 99% of them, it's more or less like my probabilistic source. There's one photon every 100 pulses or whatever. But that scaling I showed really starts to take off. Even with 25% global loss, I can start to do a lot of things with 4 photons, but I can really even think about doing things with 10 photons. Deterministic stuff is very urgent now. I just need some money. If you have some money, I'll even put your name on a plaque at the bottom.
No other questions? Okay, well then thank you, Rob, for this super interesting talk with a very catchy title. And
We can continue the discussion at the upper room.
yes, exactly.